Okay, hello data science students. Good morning. I hope you're all staying happy, healthy, and safe. I'm coming to you from my desktop this morning instead of virtual reality because I have some code examples that I want to do for this presentation, and it's just easier not to switch back and forth between the two different presentation modes. Coming to you this morning again, bright and early with another cup of dark roast. I still think I like the medium better. Not bad though, not bad. So let's think a minute about how neural networks function. Last time got sort of a conceptual introduction to how like the neuron works and how when you chain them together you get complicated results. Well, a neural network itself is a feed-forward mechanism. You put data in one side and you get data out the other side. And if you think about it, this is the same structure that you have for the individual neurons. Data goes in one side, comes out another. Data goes in one side, comes out another. And you pipeline these little atomic processing units end to end to end until you get some final output that you're interested in on the other end of the neural network. But looking at it like this, there's not a lot of, well, actually, there's no backward communication in the structure. So how does the network actually figure things out if there's no way for it to look back at what it's figured out? Well, this is what's called a feed-forward mechanism. You put data in one end, and it feeds forward and goes out the other end. So we need some sort of validation mechanism to help the network learn the patterns that it needs to recognize in order for it to fulfill whatever task that you're throwing at it. Well, keep in mind, you yourself, you're a squishy neural network. How do you learn? You learn through feedback. And I like the analogy of using flashcards. Let's say you're studying for a Spanish, German, or Japanese, or some other language test, vocabulary test in particular. A common way to study for that is to use like flashcards or something along those lines, where you have a question or vocabulary word on one side of the card, and then you have the correct response or answer on the other side of the card. So when you first pull up one of your flashcards, you look at the front, and let's say it's hola, or konnichiwa, or hello, or something like that. You make a guess as to what that word means. And then you flip the card over and you look on the back to verify that you made the right choice. But you have to make that guess first. It's your feed forward mechanism. You get your input, the word written on the front of the card, or the question on the front of the card. Then you feed forward, you do your internal computations, and you make a guess. And then once you make that guess, then you flip the card over and look at the back to see if you got it right. And if you didn't, then you use that information to adjust the way that you thought about the question or the way that you remembered it, and adjust your internal neural network. And artificial neural networks work pretty much the same way. This is a mechanism called backpropagation. So remember, each of these little neural network, or each one of these neurons in the neural network, has weights associated with each of the inputs going into one of the neurons, and then a bias factor that's added to the output of each of these neurons in your neural network. So what ends up happening is you perform a guess on something that you already know the answer to. So this is practice. This is your training data if we look at it in terms of how we've previously talked about models. So you put a guess in, you process it, you get your output, and then you check that output to see if it's correct. If the output is correct, fine, awesome, you keep going. But if it's not correct, what you do is you adjust the internal weights associated with these neurons in your neural network. And then you try again. And then you continue this process over and over, homing in on an ideal or close to ideal set of weights for each of these neurons in order for the neural network to provide the output that you want. Now that's a really weird and big and almost convoluted way to say that your neural network's actually studying. That's literally what's happening here. You ask your neural network a question that you already know the answer to, and you look at the response that your neural network gives and say, oh, you got it wrong, you got to try again, or you got it right, move on to the next, and so on and so forth. And this is the general mechanism of the back propagation process. So it's a cycle of training your neural network. Now, the interesting thing here is this is somewhat of a blind process to the programmer. Once you've set up your neural network and you start training, you're not really in control of how the neural network is learning the thing that it's learning. And this is sometimes an advantage, sometimes it's a disadvantage. One of the circumstances under which this is an advantage is if you have a process that you believe is learnable, but you don't necessarily have a well-defined algorithm for, you can use a neural network to come up with a method of solving that problem. So one of the early examples of like a practical neural network being used in say like scientific experimentation. And at first I wasn't going to talk about this, but we might as well. Was to actually, and this is work by Mar and Poggio back in 1976. This is really really awesome old school work, and it's just great. And it's actually trying to determine whether or not neural networks were sufficiently complicated, because this was all hypothetical back in the day. We knew we had neurons. We didn't necessarily know that, whether or not neural networks functioned in the way that, we now know that they do in order to give us the vivid percepts that we have. So their idea was, can we replicate 3D vision using a computational neural network? So our eyes see the world from two different points of view. And if you look at old school stereograms or the sort of ViewMaster kind of discs, you see that, when you look at it and you see a 3D view, you've got one view for your right eye, another view for your left eye. And when you put those together, suddenly the images pop out. And what they did is they said, well, let's use random dot stereograms, so series of pixels. They're just black and white. And if you've seen sort of the magic eye posters, and if you don't know what a magic eye poster is, like go to Google image search, type in magic eye poster, and you'll see weird things that kind of look like this. And the cool thing is if you cross your eyes just right, suddenly a three-dimensional image will pop out of the randomness. And so they wanted to see if they could get a neural network to detect images hidden in 3D inside of these guys. So if you just looked at one of these images, you wouldn't be able to detect any three-dimensionality. If you looked at the other image, you won't be able to detect any three-dimensionality. But if you compare the two of them, suddenly shapes start appearing in depth. And what they did, they encoded the neural network as, or rather encoded the input to their neural network instead of a 2D image as a series of one-dimensional arrays. So essentially a series of ones and zeros. 1 a pixel is on, 0 a pixel is off, so on and so forth. Now this is going to be important because this is actually how you're going to want to format the data that you're going to input into your final project. And so what they did is they fed these one-dimensional arrays into a neural network and processed the output line by line. And what they found was that you could in fact replicate stereo vision characteristics using a computational neural network. And so if you cross-eye view these two columns, you get shapes that pop out that look something like this. And I apologize for the really kind of bad images here. This was a long time ago. This was not made in PDF, and printed printed to PDF like you would these days. This was printed on real actual paper and like photocopied. So the way that the neural network learned to do this was by repetition. You take training data that you know the answer to, and you feed into the neural network, and you give it that feedback, and it repeats the process, practicing over and over and over until it starts figuring out the patterns that it should be seeing in the data. Now, skipping forward. Oh, well, one of the things here, the point being is that we might not have a well-defined algorithm for how to do this, but we could see that a neural network could actually fairly easily learn how to get stereoscopic detail out of, these random dot stereograms. Now, I can't remember where I read this, and I certainly don't remember who said it, but there was a fairly famous neural network person, if I remember correctly, researcher who said something along these lines. A neural network is always going to be the second best solution to any problem. The best way to solve a problem is actually understanding the problem. So keep in mind, neural networks typically aren't going to give you an optimal solution to something. What they're going to do is give you the next best thing. So it's going to learn the patterns in the problem and maybe not necessarily come up with an efficient algorithm for solving the problem. Now, one of the disadvantages here, now in a way that's an advantage because, I might not know how to solve a stereo vision problem, but this neural network can figure it out. It's good. It helps me, the programmer, and it gives us a robust framework to work with that can solve problems on its own. The disadvantage for you, the programmer, is that the neural network can sometimes be difficult to understand because you can't directly see that solution. They tend to be black boxes. Now, this is a bit of a generalization. It is always typically going to be hard to reverse engineer what's happening in a neural network, which makes them difficult to understand. So we often tend to treat them like black boxes. We might not understand how the problem is being solved internally. Now, in our last lecture, we talked about how, in a way, a neuron in a neural network is kind of like a logic gate or a circuit component, in that you provide input to it and it provides an output out the other end of it. Now, I want to take this example sort of to the extreme, and let's actually build logic gates using a neural network. Now, granted, using a neural network to make an AND gate or an OR gate or something like that is not necessarily the most efficient thing to do, but we're using it sort of as an example to demonstrate the power of a neural network. So let's just look at these guys. This is an AND gate. So with an AND gate, what happens is you get two inputs. The inputs can either be true or false, 1 or 0, and then you get a true or false 1 or 0 out the other end. So how this works, for those of you who haven't worked with these before, I think most of you have probably seen them in some context. Let's get us some nice white text here so it'll show up on our black background. If you have A equal true and B equal true, then your output should be true. So true and true is true. However, if one of these guys is false, true and false is false. Doesn't matter if it's input A or input B. If true and false are together, the output is going to be false. Similarly, if both inputs are false, the output is going to be false. Now, if we look at the OR gate, so, kind of makes sense, if this and this are true, then whatever. This is if blank or blank is true or false, then whatever. So if we have A equals true and B equals false, as long as one of these inputs is true, the output will also be true. And, as you might expect, if both of the inputs are true, then the output will be true. The only circumstance under which the output will be false is if both A and B are false. Both of your inputs are false. So let's code. Let's see. Let's minimize this, and yeah, here we are. Okay, so first things first. If you go to the data distribution website, there is a download option for the neural network package for your final project. And if you download that, you'll get a file called data_final.zip. If we unzip this file, we get two Python files out. We get linearalgebra.py and neuro.py. If you're following along in the textbook, which you should be, these are based on the code provided in the textbook. I've made a few minor modifications to make them a little easier for us to use for a final project, but yeah, this is essentially the code that comes with the textbook. So I take no credit for the ingenuity of these guys, just their packaging. Okay, so let's start by making an example here. Let's do something. Make an example source file called gate.py because we're going to be working with logic gates. One of the important things to keep in mind is that when you're writing your code, let's refresh that. There we go. Okay. When you're writing your code, the source file that you're going to be writing your neural network in needs to be in the same root directory as these two guys, and these two guys have to be in the same directory with each other, okay? So just make sure that neuro.py and linearalgebra.py are in the same directory as, in the case of our example here, gate.py or your project.py or whatever you want to call it. First things first, you're going to want to import the Neuro package, okay? So it looks like this. And let me see here. Okay. So let's think about this in terms of our flashcard example. We're going to want to teach. We're going to pretend we're teaching a person, what the output for say an AND gate is, if we show you the inputs that it's going to be given. So let's say that we've got just go ahead and add a comment here saying AND gate example. Let's say that we're building our flashcards. And what are all the possible inputs to our AND gate? Well, there's two inputs. Each of them can have two possible states, true or false, or in this case we're just going to use 1 and 0. In that case, we're going to have 4 possible combinations. So we're going to add in the comment here that 0 equals false and 1 equals true. So what we want to do is we want to build our flashcards. We've got our deck of flashcards here. That's our flashcards list. And we're going to put 4 flashcards in here. Okay. Now you can think of these little lists here as being your individual flashcards, and this whole thing as being your deck of flashcards that you're going to be studying with. Now we're going to write on the front of these flashcards the thing or the question that we want to ask. In this case, we're going to ask, what is 0, 0? What should the output for 0, 0 to a logic gate be? And another combination would be 0, 1, 1, 0, and 1, 1. So we just wrote the questions on the front of our flashcards. So now we've got to write something on the back of our flashcards. We're going to call these our answers. And so you can think of this as being the deck of our flashcards, and then each of these lists being an individual flashcard. And then you write the response that's associated with the front of the flashcard on the back of the flashcard. So for 0, 0, and let's just space this out a little bit so just be a little bit easier for us to visually understand that these are paired with each other. So for 0, 0, 0 and 0 or false and false is going to result in an output of false. So false and false is a false statement. Similarly, false and true is also going to be false. Oops. And true and false is going to be false. The only time that an AND gate is going to give you a true output is if both of the inputs are true. So true and true gives us a true output. Okay, so now we've made the flashcards we want to practice with. Now we got to set up the brain. We got to make the student who's going to be studying this. And that student who's going to be studying this, that brain that's going to be learning this, is our neural network. So there's a function built into Neuro called setup network. And you've got to pass it your inputs, what you're going to be training it on. In this case, we're going to show our network our list of flashcards. And at this point, it's not going to be trying to learn anything. It's just going to be seeing, okay, how many flashcards have we got? How big are the questions on the front of the flashcard? Okay, based on that, I'm going to guess how complicated I need to make the brain, make the student who's going to be learning this. And this is our network. So the setup network function returns a data structure that is the neural network that's going to be learning how to answer these questions. Okay. So the next thing you have to do is, well, you've got to study. So you've got to train your neural network, training and studying, just like you guys. In order to learn something, you've got to train yourself on it. You've got to study, you've got to study, you've got to study. And the train function takes your network as input, so the brain, the student that's going to be learning this, and it's going to take those flashcards. This is where the network starts practicing. So our flashcards, and then the answers to those flashcards. The other thing that it's going to be learning, or the other thing that you need for learning is, well, let's think about this. If you're looking at flashcards, how are you going to figure out what to do? Or how are you going to figure out the patterns on the flashcards? You're not just going to thumb through them one time and be like, I understand everything now. The universe is clear to me. That's not how it works. What you have to do is you have to practice over and over and over again. So you have to do repetitions. So you've got to practice those flashcards over and over and over again. And, since this is a computer, we got to tell it what to do. We've got to tell it how many repetitions. But notice, we have networks, we have flashcards, we have answers, we don't have repetitions. So what you'll need to do is make another variable where you specify the number of times you want your neural network to practice something. This is pretty simple. Let's practice it 10 times and see how that turns out. So, your neural network is going to practice learning these patterns 10 times using these flashcards and these answers that you've defined. Next thing you want to do is you actually want to use your neural network. You want to use it to make a prediction. Well, there is a function built in this called neuro.predict. And the predict function takes two things as input. The first one is the neural network, so the brain or the student who just learned this pattern. The next thing that it's going to take is the question that you want to ask it. The question has to be in the same format as, the questions that it learned on. So in this case, we had a list of two elements, a list of a 0 or a 1 side by side. So let's practice. Let's give it that. And what it's going to do is it's going to return the numeric prediction. And we'll store that in a variable that we're going to call prediction. And let's print the prediction. Okay. And let's run our code and see what we get. So what it's going to do, just to recap, we made our flashcards, the things that we're going to train our neural network on. We made the answers to those flashcards. We set up our network. We told it how many times we want it to practice looking at these flashcards. And then we tell it to practice. We say, okay, student, look at these flashcards. Here are the list of answers, and we want you to practice this many times. And then we actually test it. We say, okay, here's the real deal. Here's your quiz. Here's your test. Here's what you need to do. So student, I'm going to give you this question, and tell me what the output is, tell me what the answer is, and store it in prediction. So let's save this and run our code. Okay, that's interesting. When we ran our code, we got something that was not a 1 or a 0. That is unexpected. Well, our neural network's actually not super smart right now, okay? We only looked at it 10 times. And if this is not a life lesson, I don't know what is. You can't just look at everything a handful of times and expect to be able to pass the test with flying colors. Your neural network is no different. And keep in mind, you are a squishy neural network, so you need to practice things more and more. Well, let's pretend that our network, maybe our network was kind of smart. Let's say we round. 0.24 isn't very big. That would round down to 0. Let's call that a win and say, it guessed a 0. Let's compare it against another test case. Let's say we're going to test it against 0, 1. So let's save that and run our code. Uh-oh. Well, 0.27, it's still less than 0.5. That rounds to 0, so let's call that a win too. Let's look for true and true, so 1 and 1. So test it with this right here. Okay, and we'll run our code and see what we get. Oh boy, well, that definitely doesn't round up to 1, so our neural network really didn't get super smart. Well, one of the things to keep in mind is that your neural network will almost never give you a definitive 1 or 0. It's going to get close, and the more you train it, the closer and closer it's going to get to 1 or 0. But it'll most likely never give you an explicit 1 or explicit 0. So you do typically have to do rounding on this. But rounding isn't going to help us here. Our neural network is pretty dumb. So what we need to do is train it up some more. Let's increase the number of repetitions to 100 and see what we get. Matter of fact, let's change this up a bit. So we're not duplicating a lot of effort. Let's make 4 test cases corresponding to the 4 possible inputs our network can get. And let's 0 and 0 equal 0 and 1 equal 1 and 0 equal and 1 and 1 equal. Okay, so let's clear our screen and run this code. Uh-oh, we made a mistake. Hey, mistakes happen. That's how we learn with our squishy neural networks. There we go. Okay, cool. Okay, so our neural network is starting to get smarter. Notice that, it's not 0, it's not 1, but all the cases where we're expecting 0 are now below 0.5. And the cases where we're expecting to see 1 is now above 0.5. So if you were rounding your output, you would actually get, the correct responses to these guys. Let's say we studied this combination of things 1,000 times. How would our neural network do? Awesome. Now you see what we're doing. We're starting to converge towards 0 and 1 for our outputs. So our neural network is actually starting to get pretty darn smart. We're very close to 0 for 0 and 0, so it's really sure that that should be a 0. And it's pretty darn sure that 0 and 1 and 1 and 0 should give us an output of 0. And for 1 and 1, it's pretty darn sure that our output should be 1. Okay, now that's great. What if we wanted to train our neural network to be an OR gate? Well, this is part of the beauty of a neural network. The general structure is going to remain the same. The thing that you change is what you train your network with. So you have the flashcards and the answers associated with those flashcards. So since our OR gate, it takes the same input, 0, 1, true and false. The output is what's different. All we've got to change is the answer that we're training our network on. So for an OR gate, 0 and 0 is the only case that's going to result in a 0 output. So as long as there's a 1 in the input, we're going to want to see a 1 in the output. So as long as there's an input that is true, we get an output that's true. And so now, just by changing 3 characters, only 3 characters in our source code, we can retool this thing to behave as an OR gate. Boom, look at that. So 0 and 0 gives us a value that's very close to 0. 0 and 1, 1 and 0, 1 and 1 gives us values that are very, very close to 1. So that's pretty darn cool. That's a pretty powerful. Now granted, this is not an efficient way to make an AND gate or an OR gate, but it is really cool that we have a framework that's robust enough that with very little modification can learn to do something else independent of you writing the code to make it think the way that it thinks. So this is effectively how your final project is going to work. You're just going to encode new inputs and new outputs. And the way that you encode those is defined in our final project document. Okay, another important feature that we need to talk about with our neural network code is, this is neat that it can do all this computation and figure out patterns and things like that, but it doesn't seem very useful if we have to execute this over and over again. We have to retrain our neural network every single time we want to teach it or use it to do a particular task. Well, that is obviously an issue, and the cool thing about neural networks is you can save the network and reuse it. And this is one of the things you're going to need to do for your project. So once you've trained your neural network, you can actually save it. So there is a function called neuro.write network to file. And it takes 2 parameters. The first parameter is the name of the file you want to write. So you can say write it to something called like mynetwork.net, and you want to write your network that you created, this guy that you created here and that you've trained here, you want to save to a file here. And so if we save that, now we go over here and we run our code, we get the same output, but now we have mynetwork.net, and this is an exact copy of that network that learned how to do these computations. So if you wanted to reuse that network without having to train it again, what you could do is you could go over here and actually we can comment out all of this code. And we can set our network equal to neuro.read network from file, and give it the name of our neural network file. In this case, we called it mynetwork.net. And if we save that and we run our code again, we get the same results. And this time we didn't have to go through the trouble of retraining our neural network how to recognize inputs and outputs for an OR gate. So we can train our neural network and save that trained network to a file and open it again. Now, another advantage is you can actually train your neural network, save it, open it up, and continue to train it if you want. But either way, regardless of how you go about it, for your final project, once you train your neural network how to recognize the patterns in the die faces, you're going to want to use your write network to file function to save that file, to save that neural network. And this is what you're going to upload to the testing website linked in the final project document. Look back at our slides here. Your final project is you're going to be given a low resolution picture of a die face, you know, like the dice that you roll when you're playing a game, but a single die. And you're going to want to encode this as an array of ones and zeros, where the die face is represented, the white part of the die face is represented as ones, and the dots in the die face represented as zeros. And the background of the die face is, or background behind the die, is going to be represented as zeros. And you're going to want to encode this as one single list of a bunch of ones and zeros, so that this part of your list, or this part of your die picture, is going to be associated with that part of your list. So you concatenate each of these guys end to end, this row to this row to this row. So you can see that guy associates with this part of your list, and this guy goes with that part of your list, and you just keep concatenating each of these rows end to end to end as a single list. And this is the input that you're going to train your neural network with. I'm going to give you regular test cases and tricky test cases. These are your regular test cases. Your typical die faces, all perfectly oriented, 90 degrees up, looking like this. And these are the only ones that you're required to pass. So check out the numbers that I give you in the assignment document, but these are the test cases that you're going to have to teach your neural network how to recognize. So 1, 2, 3, 4, 5, and 6. For those of you who want to compete for top places on the leaderboard, you're going to have to accommodate test cases that are offset by intervals of 45 degrees. So here are some examples. Since this is for bonus points only and for prestige on the leaderboard, I'm not going to give you all of the test cases. I'm just going to give you these examples, and you need to work out the rest. An important thing to keep in mind that for all test cases, regular and the tricky ones, so these are your tricky test cases, these are your regular test cases, is that the die can be located anywhere inside of this 10 by 10 picture, this 10 by 10 grid of ones and zeros. So a few tips. You can generate your data any way you want as long as you produced it, okay? This means that if you want to write it out by hand on a piece of paper and transcribe it into a text file, that's your prerogative. You can do that. You can make a spreadsheet or CSV and edit it in Excel to make it. That's fine. Or the preferred way that's going to make life easier for you is if you can write a program to generate your test data. Make sure that your training cases are lists inside of a list. Just like our flashcard, each of those die faces is going to be a single flashcard inside of your deck of flashcards. Okay, and also make sure that all of your lists are exactly 100 elements long. So a 10 by 10 image of on and off pixels, 10 times 10, going to give you 100. One of the frustrations of doing this by hand is that sometimes you, the person typing stuff in, can make a mistake and leave off perhaps a number. When you encode the response for each of these, I want you to encode it as, say, if it's a four-sided or a four side of the die, and code the output of that as a 0.4. So everything needs to be on the scale of 0 to 1. And so if it's a 1 on the side of the die that's facing up, you want the output to be a 0.1. If it's a 6, you want it to be a 0.6. So on that note, don't forget to scale your targets or the answers for your flashcards to be on the 0 to 1 scale. So a 1 is going to equate to a 0.1, a 2 is going to equate to a 0.2, a 3 is going to equate to a 0.3, so on and so forth. So these are the values that you're going to want to put as the answers to your flashcards. And these are going to be the flashcards that you set up in your program. How many repetitions you're going to need to train this on? I don't know. It depends on how well you train it, or how well you make your training data. But it's going to be at least 100. There's not going to be pretty much any circumstance where you're going to need to train it for less than that. Okay, so be absolutely certain that your inputs and targets exactly match the format that we specify in the assignment document. Otherwise, when you upload it to the testing website, it's not going to work. Data suggestions, yeah, this is pretty much what we already talked about. If you want to make this and make your training data in Excel, it might help to turn on conditional formatting so you can easily visualize where your ones and zeros are. If you do it by text, you can do it by hand, by typing into a text or CSV file. But this is probably the most reliable way to do it. If you can come up with a programmatic way to generate your test cases, or rather your training data, this is what you're going to want to do. How I did it, I've implemented this two different ways. One is using pretending that it actually is an image, and we have an image of a die that we move around inside of an image that's a 10 by 10 background. The other way is, you could do this as like a text processing kind of problem where you're shifting arrays of ones and zeros around inside of a list. However you want to solve it is fine with me. The point of this assignment is for you to generate good testing or good training data so that you can make a smart neural network. And with that said, we're going to wrap it up. If you have any questions, please let me know, and look forward to seeing your solutions to your final challenge. Take care, folks. Stay happy, healthy, and safe, and wash your hands.